So this is a video about homeostasis. We're talking about a couple examples of things that we've already talked about, but give a little bit more detail and make sure that you understand how that connects to this idea. But we're going to talk about a couple other examples of homeostasis. So to begin with, we should define the term. So homeostasis is all about um, keeping well, at least homeostasis for humans is keeping our bodies um, within what we call normal limits. So our body operates best within certain limits, and homeostasis is a way. It's the ways in which we keep those things within normal limits. So just to give you some examples of things that we have to keep within normal limits, and this is a small subset of um, what we of everything that we have to keep within in homeostatic control. Um, Blood pH. We've got CO2 concentration, which are a couple of things that we've talked about um, fairly recently, and we've talked about how the medulla oblongata is something that helps control this homeostatic control of both blood pH and carbon dioxide concentration. Although there's more detail, especially with the blood pH, um, but you should know that the medulla oblongata increases the heart rate by sending a signal through the nervous system, namely the cardiac nerve, to the heart to increase the heart rate, thereby increasing the rate by which deoxygenated or blood with higher amounts of carbon dioxide reach the lungs, and therefore the carbon dioxide can diffuse out of the lungs into the alveoli, and then you can exhale that excess carbon dioxide and get rid of it. And then when it has lowered the amount of carbon dioxide in the blood, the medulla oblongata sends a signal through the vagus nerve to the heart to slow the heart rate back down. But other examples that we'll be talking about today, I'm going to put this in a slightly different color. Maybe I could do that in a drastically different color. Now I'll talk about a little bit more in detail our blood glucose concentrations, as well as body temperature. These are the two that I'll talk about in greater detail today, and I'll also mention the importance of water balance within tissues. But this is really about regulating, let me spell it right, regulating water movement across cell tissue, or cell membrane. And if you are thinking about your IA or possible IA topics, one of these, osmosis, should be ringing a bell. Anyways, we'll talk more about this a little later in a future unit. So let's talk about blood glucose concentrations and body temperature. But we'll talk about body temperature before blood glucose concentration. But before that, we'll actually talk about how your body controls itself. So how does your body know what to do and when to do it? And there are two major systems. There's the nervous system, which includes the central nervous system, which we'll learn more about, so you don't need to know this detail of the central nervous system quite yet. there's the central nervous system and the peripheral nervous system. I just want to give you some context for when we come back and talk about this a little later. So we've got the central and peripheral nervous system, and there are other branches like autonomic and non-autonomic phases or systems. But these actually work in tandem, in some sense, with hormones that are controlled by the endocrine system. And basically, the endocrine system is a network of glands that produce different hormones or proteins that are released into the blood, targeted for certain types of tissue or collection of cells that need to read those hormones and then act upon those hormonal signals. But this endocrine system utilizes the circulatory system to get those hormones around the body. But the intersection of these two are really, it's really what's interesting, because it's the hypothalamus in your brainstem. Hypothalamus is what intersects these two systems and determines which system to use to send certain signals. Alright, so that's the hypothalamus, not the medulla oblongata. Okay, so let's talk about temperature control. Body temperature control. Alright, so what I think is important to understand here is that we've got our normal body temperature, which you know as 98.6 degrees Fahrenheit. Please never ever forget this unit. Remember, we're in IB, and many other countries that may be reading your test or any other materials may not be using Fahrenheit. So you should also know that's 30 degrees Celsius. I wouldn't worry about Kelvin. We won't remember those units. So let's say that your body is getting to be too hot. Let's go with that example first. So remember, this is all about homeostatic control and how your body reacts to control the body temperature and keep it within normal limits. So our body temperature is never exactly these numbers, but it's relatively close. And we know that when body temperature increases, what potentially happens is, what will happen is the denaturation of proteins and enzymes, which are a type of protein, and that would kill us. So we have to keep our body temperature within this, well within a narrow range. So anyways, when our body heats up, what ends up happening is that the thermoreceptors, there are thermoreceptors. These are special type of sensory cells in our skin, thermoreceptors in our skin, signal the hypothalamus. They signal the hypothalamus, and basically what they do is they trigger cooling mechanisms, and some of those things are increasing sweat production at the sweat glands, so that there could be some cooling. There's also dilation or dilated arterioles or larger arteries, dilation of blood vessels to increase blood flow to the skin. And this is simply because one of the things that blood carries is heat, which is a byproduct of cellular respiration. Remember, cellular respiration is glucose plus oxygen yielding carbon dioxide, water, and ATP, and it also gives off a little bit of heat. So the more heat that we can get to the skin to radiate out, so this is evaporative cooling. Let me add that. Evaporative cooling. And this is radiation loss. Let me make sure that this is, yep. And, okay, so basically then what happens is that the body temperature decreases. So the temperature comes back down to this lower number. But what can happen is that the body temperature can decrease. It can also go down too low. So body temperature cools down. And this could be for a whole host of reasons. Perhaps your cellular respiration rate is low. Perhaps the environment has changed. Same with heating up. The environment could be warmer. You could be exercising, and your cellular respiration rate has gone up. Whatever the case may be, the temperature is going up or it's going down. And what ends up happening again is the same thermoreceptors in the skin trigger the hypothalamus. And this is done with your nervous system. This triggering the hypothalamus. And this triggers shivering, which is basically your muscles constantly contracting and releasing, trying to increase the rate of cellular respiration, using up more glucose, using more oxygen to give off ATP and namely heat. Triggers shivering and vasoconstriction, which is constricting or tightening up of blood vessels and vaso, thereby preventing blood to flow in high volume to skin, reducing heat loss. You could also think of this as the blood is being retained into your core to keep your vital organs at the normal body temperature. But it has a warming effect, and then what ends up happening is that the body heats up. Okay? So this is sometimes what we call a feedback loop, and this is one example. So I'm gonna make a quick note here. Feedback loop. And so that feedback loop is often called a negative feedback loop. So when there's too much or too little of something, there's a negative feedback loop to bring that level back to normal. It's not a runaway effect. A positive feedback loop would say, oh, okay, this happened, so we're going to trigger more of it by doing this. And it's a runaway effect, which we have very few examples of positive feedback loops. Most of our feedback loops, because of homeostasis and keeping things within normal limits, are considered negative feedback loops. Because it puts things into check and brings that back to the normal limit. Okay? So that's temperature control. Let's talk very quickly about blood glucose. Oops, I can spell. Blood glucose concentration. So this is also very similar, although there are a few other details that you need to know. So let's put here in the middle our normal blood glucose concentration. Now, you don't need to know what that normal blood glucose concentration is. You don't need to know that value. The only reason I gave you the body temperature one is because that's something you know already. But you need to understand how this works. So, basically what blood glucose is the amount of glucose that's been dissolved into the plasma. And remember that we get glucose into our bloodstream through the villi, into the capillary bed that's sitting within the villi of the small intestines. Something that we did not talk about is that glucose from the villi goes directly to the liver, and the liver is sensing the amount of concentration of glucose in that blood, and then doing something about it. So, and know that glucose concentration fluctuates several times a day. Whenever you eat, not right when you eat, but when that food it's down to the small intestine, blood glucose levels spike because it's rushing into the bloodstream, and then it'll drop through the day as you use that glucose throughout your cells, throughout your body and each of the cells, and then it spikes again when you eat. So we have to be able to regulate that blood glucose concentration so it doesn't spike, drop, spike, drop, spike, drop. It needs to stay within a normal limit. And this is what we're talking about, and how we do that. But remember that this glucose is important for cellular respiration again, because it's one of the reactants in the equation, and we need it to make ATP. So that vein that takes the glucose to the liver is what's really regulating the amount of glucose concentration in the blood. So let's talk about what happens when the blood glucose concentration goes too high. And this would be simply because you ate a diet, you had some food that was high in the glycemic index, something that was really sugary or even fatty, that increases the amount of blood glucose or other particulates in your blood. So what happens? So the liver triggers, I guess I can write this out so you have it, but let me write it in a slightly different color. So the liver, let's say, signals the pancreas to release insulin. And I hope that you're thinking about diabetes here, because we'll talk about that in just a second and how that plays an impact here. We've talked about diabetes a few times. This is the mechanism that people without diabetes are able to engage into. But basically, you also need to know that it's not just the pancreas, but you also need to know that it's beta cells in the pancreas that release insulin. So it's a special type of cell in the pancreas that releases insulin. And insulin does two things. One, in that it opens up channels, so it interacts with protein channels in the cell membrane. To allow glucose into cells and therefore out of the bloodstream. And two, when it's in the liver itself, it allows for the condensation of glucose into glycogen. And you do need to know how to spell that. So you need to know that insulin does two things. It allows sugars to leave the bloodstream and go into every single cell in your body, but namely in your liver and in your muscles, it allows for that glucose to turn into glycogen and be a stored polysaccharide that can be used later. So that's one way that the glucose concentration in your blood can be reduced and come back to normal level. So it's lowered here. But it can also go to low, right? So maybe you haven't eaten in a while and you feel tired, you feel lightheaded. These are some normal symptoms of having low blood sugar, and oftentimes you need to increase that very, very quickly. So you can do that in a couple ways. You could eat food and get that there, but your body has a normal way of dealing with that, and this is really that the liver, when it senses that there's low blood glucose or blood sugar concentration, the liver signals alpha cells in the pancreas. Oops, no E on the end of that. In the pancreas to release an enzyme called glucagon. Excuse me, a hormone called glucagon. And that glucagon hydrolyzes glycogen. And so it's basically breaking down this polysaccharide that was stored in your liver and in your muscles by the insulin back into the glucose and releasing that back into the bloodstream so that we're back at normal blood glucose concentrations. I hope that makes sense. But alternatively, you can manage that as well with your diet. Okay, so let's talk about the application of this, and really what you maybe already know, maybe you don't know this, but let's talk about diabetes. So we know some of the causes of diabetes, like having a high glycemic index diet, not having enough exercise, having a low fiber diet, but these are also things that you'd recommend as dietary changes or treatments to someone who has been diagnosed with diabetes. But there's a difference between type 1 and type 2. And really, what you should know is that type 1 is autoimmune, is an autoimmune condition. And basically what that means is an autoimmune disease, rather. Basically, the immune system of the person with type 1 diabetes is attacking its own beta cells so that insulin cannot be made. And so, obviously, the treatment for this, I would write this down, I'm not going to jot it down, but the treatment for that would be insulin injections. And we can often take insulin from other organisms, like pigs, or we can take them from pigs, or there are other technologies now that we can use to make insulin, but that's what people used to use, is pig insulin, because it worked the same way and our body recognized it the same way. But anyways, those insulin injections can be used to help regulate high blood glucose concentrations. So then people with type 1 diabetes need to constantly monitor their glucose concentration, namely through doing a blood test. And if their blood sugar level gets to be high, they have to take an insulin shot. But type 2, type 2 is not autoimmune, but instead, when the body no longer responds to insulin. I guess I should note that this autoimmune condition, type 1, makes up about 10% of diabetics, and type 2 makes up about 90% of diabetics. Type 2 is sometimes referred to, and I think I mentioned this earlier, is adult onset or child onset diabetes, but we're seeing more and more children being diagnosed with diabetes. And it's also known as insulin resistant, which is essentially the idea that this insulin isn't being read by the cells that need to then allow the glucose into them. So insulin's not doing its job. So an insulin injection would not work. And so these people need to very carefully regulate their diet so that they don't have high blood glucose concentrations, and therefore probably should be eating low glycemic index foods, eating fiber-rich foods, eating smaller regular meals so they don't have the spikes in blood glucose and then drops in blood glucose. They can manage their own homeostasis of that through their diet and regulation of meal consumption. But just to review, there's some genetics that could be at play here. There could be some, and I'm not going to write the rest of this, obesity, lack of exercise, older age because the system is worn out, and I'd refer you back to the discussion on diabetes in option A that we discussed earlier. Okay, but I hope that helps, and come to class with questions. I think that's all that I have. Oh, I should note that some of this material is reviewed in some more detail, some less detail in section 6.5. It's on nerves, hormones, and homeostasis. Obviously, I didn't discuss nerves at all. We're gonna talk about nerves in greater detail when we talk about option E. So we're removing it from this section for now. So again, you're responsible for hormones and homeostasis from 6.5. Okay, I think that's all I need to talk about.